going to be on quantum lifting for invertible permutations and ideal ciphers, and Alex will give the talk.
So in this talk, I will be presenting our work on quantum lifting for invertible permutations and ideal ciphers. And this is a joint work with my amazing collaborators, Miki Han, Chipeng Liu, Takashi Yamakao, and Aram Yun. So in this presentation, we are going to work in the query model, which is this elegant abstraction that is widely used in both crypto and complexity theory. And the most famous example is the random oracle, in which several crypto systems are designed and analyzed. And in this model, we are saying that a query algorithm is trying to solve a particular problem by just querying a black box function f. And the complexity of such an algorithm is solely given by the number of queries performed to this black box function. However, as we know, the quantum computing is bringing a new query model, the quantum random oracle, in which now superposition queries to this black box function f are allowed. And as a result, this is equipping quantum parties and, more importantly, quantum adversaries with more powerful capabilities. And an even further extension to this occurs when this black box function f is a permutation. And in this case, we say that we are dealing with the quantum random permutation model, which it differs because now superposition queries to both the permutation and to its inverse are allowed. So the main ideal goal of this work would be to try to relate the security of a scheme against classical adversaries with security against quantum adversaries. And more precisely, ideally, we would like to have a lifting theorem that states something of the following type, that if we have a scheme or a security game that is secure against classical attacks, then our goal would be to try to lift it to ensure security also against quantum adversaries. And a bit more precisely, in this work, we are going to focus on establishing some lifting theorems for security search games in the quantum random permutation oracle model. So to be a bit more precise, the setting that we are going to deal with can be summarized as follows. So we have a challenger that can perform up to k classical queries to the permutation and to its inverse. And we also have a quantum adversary that can perform q quantum queries to similarly both the permutation and to its inverse. And moreover, the adversary and the challenger are allowed to exchange classical messages such that at the end, the challenger is either going to accept or reject. And we say that the adversary has won this security game if it resulted in the challenger accepting. So this notion of lifting theorem in the random oracle model was initially introduced by Yamakao and Zandri as a tool that enables lifting security from the classical world, so from the classical random oracle to the quantum world, to the quantum random oracle. And at a high level, their result states that, that I'm going to, from now on, just refer to it as YZ, states that if we have a search game, G, that satisfies the following, that in this game, challenger only performs a constant number of queries to the random oracle. And this game G is secure against a classical adversary, then this game also becomes secure against a quantum adversary, so in the quantum random oracle. And a bit more concretely, we say that the result states that if we have a challenger that makes k classical queries, and for an arbitrary quantum adversary that makes q quantum queries can win this game with probability epsilon, then one can also construct a classical adversary that only needs to perform k classical queries, so the same number of queries as the challenger, that can win this game with probability at least the probability of the arbitrary adversary, so epsilon divided by 2q plus 1 to the power of 2k. As we mentioned, our main result would be establishing some lifting theorems, but this time in the quantum random permutation model and in the quantum ideal cipher model. And at this stage, you may wonder why these lifting theorems are particularly useful. Well, at a high level, because they essentially tell us that if we want to study the security of such a search game against an arbitrary adversary, well, then it just suffices to study the security against a classical adversary that only needs to perform a small fixed number of classical queries. And a bit more concretely, as we mentioned, in this work, we are going to deal with these two models, the query permutation model, in which, as we said, every algorithm, every adversary has access to both the permutation and to its inverse for a uniformly random permutation. And in the ideal cipher model, in which every party has access to a parameterized function and to its inverse, where each such parameterized function ek is an independent random permutation. And why these two models? Because, as you well know, several constructions and proofs are developed in these two models. And just to give some famous examples, this includes the Even-Mansur cipher, the Davis-Mayer hash function, and the sponge construction. And at this stage, it might be worth emphasizing a bit the distinction between the quantum random oracle and the quantum random permutation, and more precisely, why it is more challenging to work in the second model. Well, on one hand, the random functions have this very nice property of perfect independence. Namely, if we look at the outputs of a random function, these are always going to be pairwise independent. But on the other hand, if we look at the random permutation, the outputs are going to be almost independent. But it is exactly these weak correlations between the outputs that invalidate all the methods we know how to use in the quantum random oracle. And I should mention that this issue of weak correlations occurs even when the algorithm has access only to the forward permutation and not to its inverse. But moreover, as we have seen in the definition of the two models, in these two models, the algorithm has access to both the permutation and to its inverse. And when the algorithm has access to the backward permutation, so to the inverse, this destroys the independence, making it extremely challenging to extend all the proofs we are currently using in the quantum random oracle. So as we mentioned, our main result is a lifting theorem in the quantum random permutation model that can be summarized as follows. So if in this game we have a challenger that can perform up to k classical queries to the permutation and to its inverse, then for any arbitrary quantum adversary that makes q quantum queries to the permutation and to pi-1, we can construct a classical adversary B that makes only k classical queries, so the same number of queries as the challenger, that can win this security search game with probability, at least the probability of the arbitrary adversary A divided by this quantity over here. And as we said, this is extremely useful because now it essentially tells us that if we want to study the security of such search games against an arbitrary adversary, well, then it just suffices to study the security against an adversary that only performs this small fixed number of classical queries, which, as mentioned, it's exactly the same number of queries as the challenger performs in the original game. And now I just want to mention like some applications of these lifting theorems. So on one hand, it allows us to derive some new quantum query complexity bounds, but we can also use it to derive new post-quantum security results. So on one hand, we can show some tight bounds for the quantum hardness of the double-sided zero search game problem, which I'm going to describe in a minute. But we can also use it to show the post-quantum security for properties such as pre-image resistance, one-wayness, and multi-collision resistance for constant round sponge, but also for the collision resistance of the Davis-Mayer. So now let's revisit these applications a bit more carefully. So for the double-sided zero search game, so in this problem, we are given a permutation pi acting on two n-bit strings, and the algorithm has access to both the permutation and to its inverse. And the task is to find the pair xy such that pi of x is equal to y, and moreover, x and y need to have at least n leading zeros. And by directly applying our quantum lifting theorem, well, then it is quite clear that k is equal to 1, as the challenger only needs to make a single query to the random permutation, the query in which verifies the solution given by the adversary. And therefore, by our lifting theorem, it actually just suffices to study the hardness of this problem for an adversary that makes one classical query. And for such an adversary, it's quite clear that it can solve this problem with probability at most 2 divided by 2 to the n, where this comes from two situations that either the algorithm queries a valid pair or it just correctly guesses one. And then by directly applying our lifting theorem, we can show that for any arbitrary adversary that makes q quantum queries, it can solve this problem with probability at most q squared divided by 2 to the n, which we also know it's a tight bound due to a result of Caroline-Poremba. And moreover, we can also generalize it to an arbitrary game GR parameterized by some relation R, where the task is to find a pair xy in this relation. And for such a problem, we can show that if an algorithm has q quantum queries, it can solve this problem with probability at most q squared multiplied by the probability of finding such a pair in this arbitrary relation R when given one classical query, which we also know it's a tight bound due to Grover search. But as we mentioned, we can also use this lifting theorem to derive the quantum security of different cryptographic tasks. And on one hand, we can apply it to the sponge construction, which, as you know, is this famous permutation-based hashing algorithm that underlines SHA-3. And just to revisit a bit the history, so in the classical world, we know that the sponge construction is as secure as a random oracle, but in the quantum world, not that much is known. So on one hand, we know that single round sponge satisfies pre-image resistance and one-wayness, but also resetting differentiability in certain parameter thresholds. But prior to our work, no results were known about multi-round sponge. And it turns out that by directly applying our lifting theorem, we can just reduce the post-quantum security to classical security for sponge. And this allows us to derive some non-trivial but not tight bounds for constant round sponge. So as mentioned, for properties such as pre-image resistance, one-wayness, and multi-collision resistance. And here I want to emphasize that concurrently, a really nice work of Alok H. Carolan, Magenza, and Tokat also showed quantum indifferentiability for multi-round sponge, but via a very different route. And we can also use our lifting for the Davis-Meyer and PGV hash functions, which are these block ciphers hashing underlying SHA-1, SHA-2, and MD5. And similarly, in the classical world, we know that this construction satisfies the one-wayness and collision resistance in the ideal cipher model, but in the quantum world, only one-wayness was proven while collision resistance was still open. And again, it turns out that by just directly applying our lifting theorem, we can show the collision resistance of the Davis-Meyer. And as you might guess, the analysis is not very specific to this. We can also apply it to like other PGV hash functions. And in the remaining minutes, I just want to mention a bit about the techniques and tools used to prove our result. So just to set the notation for a reprogrammed oracle to output y on an input x, we are going to use this notation over here, hxy, which simply on input x is going to output y, and on any other input is just going to act as the original oracle h. And to understand better how this can be proven, it is going to be useful to revisit the YZ lifting theorem in the random oracle case. And for this, we can just simply focus on the function inversion task, in which the task is given access to a random oracle h to find the preimage of all 0. And it is quite clear that for such an adversary that is trying to solve this problem, that is going to output some outcome x star, there are only two cases. Either x star was queried by at some point, or x star was never queried. And for this reason, we can denote by I star the index of the query at which A has queried this outcome, and we simply say that this index is going to be bought if x star has never been queried. And then the very nice observation in YZ that enabled them to derive the lifting theorem is that such an algorithm cannot distinguish between the following two situations. So in the first situation, the algorithm A has oracle access to the reprogrammed oracle, reprogrammed on the outcome x star from the very beginning, so for all its queries. And in the second case, A has oracle access to the original oracle up to the point of querying x star, and then has access to the reprogrammed oracle for the remaining queries. And it is quite clear that such an algorithm cannot distinguish between the following two situations. And as a result of this observation, YZ was able to define a simulator that essentially simulates the outcome of A that has oracle access to the reprogrammed oracle. But unfortunately, this very nice and natural approach fails even in the classical random permutation model. And for the reference, we are going to relate back to the double-sided search problem. And ideally, we would like to argue that if we use the previous simulator that YZ defined, then the simulator is going to behave similarly to the output of A having oracle access to the reprogrammed permutation. But this is false due to the weak dependencies that are inside the permutations. And to make this a bit more concrete, you can imagine the following scenario. Imagine that the simulator succeeded, so it correctly guessed the index of the query at which x star has been queried. But even in this case, it is still possible that some previous query resulted exactly in the reprogrammed output. So in other words, it is still possible that the original permutation pi applied to some previous query resulted exactly in the reprogrammed value. But in this case, then the resulting function is not even going to be a permutation anymore, because it is quite clear that we are going to have a collision. And moreover, the algorithm A is able to detect such inconsistency because it notices that there are like two queries, x prime and x in our notation, that are going to produce exactly the same output, which contradicts the entire injective structure. And of course, this issue becomes even more annoying when the algorithm has access to the inverse permutation as well, which makes all these inconsistencies way easier to detect. And to kind of like deal with this issue, our solution is just to reprogram in a more careful way. In particular, we need to pay special attention to some special type of queries. And this type of queries can be summarized as follows. So we call X a hit query with respect to the outcome, simply if this query is going to be the outcome to be reprogrammed. And on the other hand, we call X a miss query if this X evaluated on the original permutation is going to result in exactly the reprogrammed value, which corresponds exactly to the collision situation we have seen previously. And therefore, when we are doing the reprogramming, according to this reprogramming rule that we still want to have, we have to do it in a more careful way in order to maintain injectivity. And for this reason, when we are doing the reprogramming, we need to take into account the hit and the miss queries. So therefore, the reprogramming permutation is going to look as follows. So if X is going to be a hit query, then we are going to simply output the reprogrammed output, so pi star of X star. On the other hand, if X is a miss, then we are going to output the original permutation pi evaluated on X star to maintain injectivity, and otherwise we are going to output the original permutation. And just to kind of like summarize, so we notice that if we just hard code the reprogramming rule as we have here, then we can violate the injectivity of the permutation. And therefore, to maintain injectivity, we need to reprogram both the hit and the miss queries. And similar reprogrammings, but I haven't included them here, need to be done for backward queries. And therefore, when we are considering like the simulator now, we notice that we not only need to guess the index at which the outcome has been queried, but we also need to guess whether this query has been a hit or a miss. And therefore, what we did is that by defining the hit and the miss queries, we can essentially capture the first query that touches exactly this outcome X star. That can happen either by querying the miss or the hit queries. And with this idea in the classical setting, it turns out we can also generalize it to the quantum setting. So we first establish a classical lifting theorem, and then we can also generalize this simulator to work in the quantum setting, which then in turn enables us to derive a measurement reprogram in the quantum random permutation model. And just I'm going to mention how this measurement reprogram lemma looks like. So here, given two permutations pi and pi star, and some arbitrary adversary A that performs Q quantum queries to the permutation and to its inverse, and some arbitrary input vector X star and some arbitrary output vector Y star, we can construct a simulator that can essentially simulate the output of A that has oracle access to the reprogrammed permutation. And the success probability of such a simulator is going to be at least the success probability of the algorithm A with access to the reprogrammed permutation divided by 8q plus 1 to the power of 2k. And now just to mention a summary of this and maybe some potential future directions. So on one hand, we derive these lifting theorems for the security in the quantum random permutation and ideal cipher models. And we show that we can use it to derive some tight bounds for the quantum hardness of the double-sided zero-search game. But we can also use it to derive some post-quantum security results applicable to constant round sponge as well as Davis-Meyer construction. And as some future directions, it could be maybe interesting to extend this to like some NISQ settings, but also to get some tighter results when it comes to like optimal security and some other complexity results. And of course, maybe some other potential applications that rely on permutations. Thank you.
We have time for a few questions.
Hi, thank you for the talk. Maybe you said something, but do you have an example, a clear example where the lifting theorem doesn't give you a tight bound?
So even for like the sponge construction, we actually don't get, we get like some new bounds, but we know that those are not tight. So the only tight bound, as we said, we are getting for the double-sided zero-search game, which maybe indicates that in general, this is a tight bound, but when it's applicable to like different post-quantum results, then in that case, yeah, we also have like some non-tight bounds. So yeah, there is room for improvement in that sense.
Okay, any other questions? Okay, if not, let's thank the speaker again.